All right, we're going to pick up where we left off, talking about chapter 16. So today we're going to do sections 2 and 3, wave speed, and then section 3 is Doppler effect. So, and I think the speed of sound. So, in this section, start out, we talk about the speed of a wave on a string. If there are any musicians among you who play a stringed instrument, guitar or violin or even piano, this should, I think, make sense. What we have here is that the velocity or the speed of a wave on a string is the square root of the tension of the string divided by the mass per unit length. So while the exact derivation of that, tension over mass, may not make sense, it does, I think, make sense when you think about the relationship. Okay, it's saying that if we increase the string tension, then the speed of the wave will increase. So in other words, in the stringed instrument example, if you have a higher tension string, you get a higher sound, a higher frequency sound. On the other hand, if you increase the mass of the string, then you get a lower frequency sound. Okay, the wave speed decreases. So you can think of this in terms of the guitar or the cello or the violin or whatever. The heavier strings on those instruments tend to have a lower sound, a lower frequency sound, and the higher strings tend to have a higher frequency sound. And as you're tuning those instruments, as you increase the tension, the pitch goes up, and as you decrease the tension, the pitch goes down. So all of that is a function of the wave speed and how fast that wave can bounce back and forth within that string. So example number 3 says if you have a rope being held on opposite ends that's 10 meters long and has a mass of 1 kilogram, if the person at one end jerks the rope, how long before the person at the other end feels that jerk? All right, so we'll work that out using our document camera. All right, in example number 3, we've got 2 people holding this rope. And so the formula that we're going to use here is going to be V equals the square root of F over mu, where F is the force of the tension in the rope, and mu is the mass density. So mass density doesn't mean mass, so we can't use 1 kilogram. We have to do 1 kilogram divided by the length of the rope, so that the density, what we'll get is kilograms per meter. So at 1 kilogram per 10 meters, that's 0.100 kilograms per meter. So now we just need to plug in our pieces here. So if we're in part A, we're looking at 40 newtons. So our V will be the square root of 40.0 newtons over our mass density, 0.100 kilograms per meter. Going to the calculator is not really necessary here because we get 40 divided by 0.1 is 400. So we have square root of 400 newtons. It's really like Newton meters per kilogram is what it works out to be there. But then when we take the square root, because of what's inside that newton, remember what newtons are kilograms times meters per second squared. So when we take the square root of that, the squared on the seconds goes away, the kilograms cancel out. We end up with V equals 20.0 meters per second. All right, so then in part B, we have almost exactly the same thing, only 10 newtons now as the tension over 0.100 kilograms per meter. And so taking that 10 divided by 0.1 part, we end up with the square root of 100 newtons times meters per kilogram. And that gives us a speed of 10.0 meters per second. Now, what we haven't done yet for either of these is we actually haven't found the time. So with a V of 20 meters per second in part A, to go 10 meters at 20 meters per second will take half a second, right? 10.0 meters over 20.0 meters per second gives us a time of 0.500 seconds. So that's the answer for that part. And then down here, taking 10 meters, dividing it by 10.0 meters per second gives us 1.00 seconds. So those are our final answers for example number 3. The heavier strings on those instruments tend to have a lower sound, a lower frequency sound, and the higher strings tend to have a higher frequency sound. And as you're tuning those instruments, as you increase the tension, the pitch goes up, and as you decrease the tension, the pitch goes down. So all of that is a function of the wave speed and how fast that wave can bounce back and forth within that string. So example number 3 says if you have a rope being held on opposite ends that's 10 meters long and has a mass of 1 kilogram, if the person at one end jerks the rope, how long before the person at the other end feels that jerk? All right, so we'll work that out using our document camera. Now, for the speed of sound, we are going to simplify things slightly like we do sometimes when things get real complicated, and we're going to assume that our atmosphere is an ideal gas, okay? Something like, pure nitrogen or pure oxygen or whatever. We know that it's not, but it drastically simplifies the calculation. So our V is going to be the square root of 1.40 kT. K is a constant called Boltzmann's constant, and T is the absolute temperature. So finally, mass is M is the mass. So we have an example of this as well. This predicts what the speed of sound will be, and it also gives us a little insight that as the temperature goes up, typically the velocity of the speed of sound goes up, or the velocity or speed goes up. As you have heavier air, then the speed would decrease. So in a really lightweight gas like helium, the speed of sound is rather high, which is part of the reason why your voice seems to be real high-pitched and squeaky when you take a hit off of a helium balloon. You get a real squeaky voice. And while it's not at all safe to do this, there are some heavy gases like I think it's hydrogen sulfide that you can fill a balloon with, and then the balloon will sink to the ground rather quickly, as opposed to a helium balloon that you've let go, it goes to the ceiling. But if you suck in some of the air out of a balloon that's got that heavier gas in it, it'll make you sound like Barry White. However, you have to be careful because that gas also settles to the bottom of your lungs. So the only time I've ever seen anybody demonstrate it, they had to have a couple of students turn them upside down in order for the gas to basically fall out of their lungs so that they didn't pass out or worse, die from suffocation. So again, not a safe thing to try. But as the air gets heavier, the sound goes down because the speed of the wave slows down. As the air mass decreases, then the speed of that wave increases, and it sounds like you have a high-pitched, squeaky voice. All right, so example number 4, we have a tuning fork with a resonant frequency of 512 hertz, and we want to figure out what's the speed and wavelength that propagates through the air if the temperature is 0 degrees Celsius and 20 degrees Celsius. So once again, we'll turn over to the document camera to work this one out as well. In example number 4, this problem is actually a little bit more of a, it's really kind of the basis for some things we're going to use later on. It basically is, in this example, we're deriving some of the constants that we're going to use later on for the speed of sound. So some of this, kind of uses assumptions or calculations that you would not be expected to come up with on your own. For example, we know that our atmosphere is roughly 80% nitrogen and roughly 20% oxygen. and there's actually lots of other small amounts of other things, but roughly speaking, 80% nitrogen, 20% oxygen gives us a pretty decent number. And if we use the molecular mass of those, the molecular mass of nitrogen is about 28, and the molecular mass of oxygen is about 32. Then what we end up with is an average molecular weight of 28.8. So basically what that means is that like an average air molecule has a mass of 28.8 atomic mass units. So if any of this sounds familiar at all, it'll be because you have taken chemistry and done some of this stuff. So basically what we're going to do with this now is we have this V equals the square root of 1.40 kT divided by m. And so 1.40 is kind of universal. For part A, when we're at 0 degrees Celsius, we're going to have V equals 1.40 times this this constant. I got to check the guy's name again. Boltzmann. This Boltzmann's constant of 1.38 times 10 to the negative 23rd joules per Kelvin times, and then the temperature here is not actually in Celsius, it's the absolute temperature in Kelvin, which at 0 degrees Celsius is 273 Kelvin. And then we're dividing by our molecular mass. So 28.8 times that atomic mass unit, where one unit is 1.66 times 10 to the negative 27th kilograms. So again, parts of this you would certainly not be expected to just come up with out of the blue on your own, such as the 28.8 number, and we have not talked about, molecular mass at all, so this is coming more or less out of the blue as far as you're concerned, probably. But what this is going to give us when we do this calculation, we get a speed of sound at 0 degrees Celsius of 332 meters per second. Which, if you're working problems in the future that deal with the speed of sound at 0 degrees Celsius, this is the number we're going to use. Okay, but actually more often, we're going to do this same calculation to see what it would be at 20 degrees Celsius, because 20 degrees Celsius is more like room temperature. That's kind of a standard comfortable temperature. So to work this again, but the only thing that changes is the temperature. So instead of 273 K, we're going to do all of this, and then this changes to become 293 K instead of 273. But every other part of this is exactly the same. So the way that changes is it goes from 332 meters per second to 344 meters per second. This will be our kind of standard speed of sound in air for most cases for us. So the only other thing that we're supposed to find here is wavelength. So for this, the wavelength is, remember that this is lambda equals V over F. Okay, so the speed of the wave divided by the frequency of the wave. So since we have 332 meters per second, 332 meters per second divided by 512 hertz, we get a wavelength of 60.648 meters, which is like 64.8 centimeters, if you'd rather write it that way. So there's our speed, and there's our wavelength. For this one down here, same formula, gives us 344 meters per second divided by 512 hertz, and that gives us a wavelength of 6.672 meters, or 67.2 centimeters. So this example, not a great example of the kinds of problems you're going to be asked to solve, really. just a good example of where we get some of the numbers that we're going to use in the future. All right, thanks. All right, so now the idea of a deep water wave. This is the kind of scenario where perhaps we have a tsunami kind of event where water's displaced because of tectonic shift. And so this deep water wave that isn't typically visible from the surface can propagate through the ocean to wreak havoc on the shore when it gets to the beach. So here we have the square root of g lambda. Remember that lambda is the wavelength. G is still our typical g of 9.8 meters per second squared. And then, of course, you guys are familiar with pi. So our example for that, speed of a deep water wave with a wavelength of 2 meters and a wavelength of 5 meters. For example number 5, we're looking at this deep water waves idea. So imagine you have a wave out in the middle of the ocean where it's very deep. Okay, so the ocean floor cannot be affecting the size of these waves. It's just too far away. So what we want to try to figure out is what's going to be the speed of these waves. Actually, let me change marker colors here to match what I've already got. V equals the square root of g lambda over 2 pi. So for our first one, for part A, we have v equals the square root of 9.8 meters per second squared times our wavelength 2.00 meters divided by 2 pi. What that gives us is 1.77 meters per second. And then if we calculate it a second time for part B, the only thing that changes, that stays the same. This part now becomes 5.00 meters over 2 pi. I guess I'm being lazy. I can write that out. It's not that much. 9.8 meters per second squared times 5.00 meters all over 2 pi gives us 2.79 meters per second. So the longer the wavelength, the faster the wave. Section 3, moving sources and observers. What happens when you're transmitting a sound and that source of transmission is moving, or perhaps the person who's hearing the sound is moving relative to where that sound is coming from. And you guys may be familiar with this. The sound of an approaching car, even if it's not honking its horn or anything, you can just hear the sound of the tires on the road or the engine noise. It sounds higher pitched as it approaches you, and then as it passes you and is going away from you, the pitch of that noise, of that sound, seems to decrease. So have a little video within a video. I'm not going to play it here. You guys will have access to these slides. You can play this video on your own. I don't know how a video within a video would look, so I'll let you guys watch that on your own. So we have a few formulas here that we're going to use. One is if the source of the sound is stationary but the observer is moving. And in that case, if the observer is moving toward the source, we use a plus sign. So it would be 1 plus V naught over V. And then if the observer is moving away, we use 1 minus V naught over V. The moving source, stationary observer. So this time the person that's listening is standing still, and the source is moving either away or toward the observer. And again, we use a plus if the source is moving toward, minus if it's moving away. And then notice that we've got O's and S's. I didn't point this out. I think I might have said V naught. But technically on this last slide, it's a VO for observer, velocity of the observer, not velocity 0, not V0. V, just regular V, is the wave speed, by the way. So now we've got if both are moving, so perhaps the source and the observer are moving in the same direction, but one is gaining on the other or losing ground, or they could be moving in opposite directions toward each other or opposite directions away from each other. Any number of possibilities out there. But basically the way I've arranged this is if they're moving toward each other, you use the plus sign on the top and the minus sign in the bottom. So in other words, the symbols that are on the top. And then 1 minus V naught over V and 1 plus Vs over V if they're moving away from each other. So use the lower set of signs if they're moving away from each other. So hopefully that makes sense. Those kind of go together in groups. It'd be 1 plus in the top going with 1 minus in the bottom. And then if you have away, it'd be 1 minus in the top, 1 plus in the bottom. We have an example here, number 6, to help us figure this out. Train and a highway are parallel to each other. So you have a train that's moving 35 meters per second, a car is moving 30 meters per second, and they're going in opposite directions toward one another. Okay, so they're not moving, the train and the road are parallel, but they're not moving in the same direction, they're moving in opposite directions. So as the car is approaching the train, the driver hears 650 hertz from the train whistle. So part A, what we want to figure out, what's the actual frequency that people are hearing from the train, and then after the train passes, what is the frequency that's heard by the driver after they're moving away from each other. So those are our objectives here. For example, number 6, we'll switch over to the document camera to look at that. All right, for our 6th example of chapter 16, we're looking at the Doppler effect. So we have a train and a car that are moving toward each other on parallel tracks. And so the driver of the car hears the whistle of the train at 650 hertz. We want to know, what is the frequency of the whistle according to the passengers on the train? So in this formula, frequency of the observer equals frequency of the source over 1. In this case, because they're moving toward each other, we'll use plus in the top, V of the observer over V, and then minus in the bottom, Vs, speed of the stationary, over V. Now, one thing that you might like better than this, sorry, I moved my paper around, it's old habit. One of the things that you might want to do here, if this formula just seems a little, I don't know, daunting, ugly, cumbersome, inconvenient, I don't know, whatever. What you might want to do is multiply this by V over V, because then what that would give you is Fs V plus V of the observer over V minus V of the stationary. It gives you the same value, and it's actually maybe a little bit easier to calculate. So in this case, our FO, our frequency that the observer hears or experiences, is 650 hertz, which will be equal to the frequency for our stationary people. Those would be the people on the train, because from the perspective of the people on the train's not moving. This would give us 344 plus speed of the car, which is 30.0 meters per second, over 344 minus the speed of the train, which would be 35 meters per second. So we do the math on this, we end up with 650 hertz equals 1.21 times the frequency of, according to the stationary position. So to solve for Fs, 650 divided by 1.21 gives us a frequency of 537 hertz. All right, so that's the answer to part A. Should have labeled, I guess, part A. 537 hertz is the frequency of the whistle according to people on the train. And then for part B, the frequency after the train passes, this is again according to the driver of the car. So this time we'll say that FO is our unknown piece. We're now going to switch to minus in the top. So 1 minus V naught, or V, I was going to say not, 1 minus VO over V, or we could say V minus VO over V plus VO, which gives us 537 hertz. That's what we just found a moment ago. And then our 344 minus, now the velocity of the car would be 30, still 30 meters per second, over 344 plus the speed of the train, which is still 35.0 meters per second. And so that gives us, if we do the math on that, 445 hertz. So we get that that Doppler effect as the train approaches the car, or as the car approaches the train, whichever you want to think of it, they approach each other. The driver of the car experiences 650 hertz. This is perceived frequency. The true frequency is 537 hertz. True according to what it sounds like on the train at the source. And then the Doppler effect causes that sound to go from an apparent 650 hertz to an apparent 445 hertz as the train and the car are departing one another. All right, that finishes example 6. The electromagnetic Doppler effect means that the Doppler effect also applies to light waves. We haven't talked a whole lot about light, but light is kind of an odd subject. It actually behaves in 2 different ways at once. One of those 2 ways is as a wave. So it's worth pointing out here that the Doppler effect also affects light waves. And here C represents the speed of light. So this time we have 1 plus V over C versus 1 minus V over C. One of the things that this is used for, well, you may have heard the term redshift. One of the ways that scientists know that our universe is expanding is because stars that are really far away from us, or galaxies that are really far away from us, their light appears to be more red. And so by comparing the light frequencies, the light waves from more distant objects that are moving away from us as opposed to other objects that are maybe moving toward us or moving in roughly the same direction we're moving, they can tell that some of these galaxies and stars are getting further away from us. So that's the Doppler effect as it pertains to light. Things have to be moving very, very fast in order for it to be detectable, though. That's why you see here I have that V is less than C. The 2 less thans together mean that V is very much less than C because of how fast the speed of light actually is. But if V is not reasonably high, I mean, V's got to be pretty high in order for us to notice a change in the light shift. So anyway, that's the electromagnetic Doppler effect. Last thing in this section, I believe, last thing in this section is supersonic speeds. So you may have seen videos of like Navy jets flying low over the surface of the ocean, and they create this big wave. The shock wave coming off of the jet produces a wave well behind the jet itself. And the idea behind that is that the sound that's trying to escape that jet. I mean, we know that jets make a lot of noise. The jet's going faster than the sound can go as it makes that sound, as it makes that noise. So all of the sound that comes off of that jet actually ends up falling behind it. And so you get, on this far right-hand picture, you get this shock wave, basically. And the thing about it is it has really nothing to do with, like, the intensity of the shock wave or the sonic boom doesn't have a whole lot to do with how noisy the jet was to begin with. I mean, it's related, but what ends up happening, if you notice inside that dotted area, okay, so right in here, as I move my cursor, notice how all of those like the edges of all of these circles are kind of stacked up. So you get this sort of dark greenish blue area from the circles, both on the top and the bottom. What that high concentration of green or blue indicates is that a whole bunch of these sound waves are all pushing against each other in a very, very tight space. Out here on the first one, we notice that these green lines are pretty close together out front, but then after that they spread out. So, if this is an airplane flying over your head and you're standing down here, these waves are all pretty far apart that are hitting you, and so the intensity of that sound is not terribly great. Same thing if they're moving at slightly supersonic speeds, but as you get to greater and greater speeds, these circles, the edges of these circles, will start to stack up and get more concentrated, and so that's where you get potentially harmful sonic booms. So if you've never watched a video of supersonic aircraft or something making a sonic boom as it goes by, it's worth checking out. There's a lot of YouTube videos out there you can look at. It's an interesting phenomenon, and this is what's causing it. All these waves are just kind of stacking up against each other and creating a really high intensity wave front. All right, so next time we'll cover power and intensity and talk about the decibel scale, and then the section, I think we're skipping section 5. Section 6 will be the last one that we do from chapter 16. I'm planning on going over those two things in one video. That'll be our next video lesson. So just kind of keep your eye on the schedule and on the release of these video lessons so that you can hopefully keep up and work on your web assigned stuff too. All right, thanks. Hope you guys have a good day.